Most hardware platforms are highly modular such that you can plug into the same system a very wide array of different I/O devices. The challenge this presents is that basically every device out there expects to be talked to in its own particular way. Therefore, when we create an operating system, unless we want that operating system to run on just one very specific configuration of hardware, well, we're going to need the operating system to be, in some sense, modular, because for each unique I/O device, we're going to need to plug in the code that knows how to talk to that particular device. These pieces of code are called device drivers. An individual driver knows how to drive, how to control one particular device. An interesting question is who's going to write all of these device drivers? Well, very often it's the manufacturer of the device who ends up writing the device driver. So for example, if you're using an NVIDIA graphics card on Windows, NVIDIA is mainly responsible for writing that driver, not Microsoft. This is true with most drivers on Windows. It's in the manufacturer's interest to make sure that their hardware works with Windows, therefore they're going to make sure that a driver exists. The device manufacturers generally don't have the same incentive when it comes to Linux. For many kinds of devices, they may not have enough customers who want to run Linux with that device anyway, so they don't bother to create a driver. Very often then, in Linux, the task of writing drivers falls to the people who develop the Linux operating system itself. So we've established that at the heart of what an operating system does is run programs, which it calls processes, and it makes sure that these processes don't conflict in their use of the hardware. Well, the most obvious kind of conflict is when you're running multiple programs and trying to get them to share one CPU. At any discrete moment of time, a single processor can only be executing code from the OS or code from one individual process. So here, for example, imagine we're running 3 processes, A, B, and C, and as those processes run, the operating system may need to do its own business as well, so it needs its own time on the CPU. So what needs to happen is that as time progresses, the CPU alternates between these tasks. Quite typically in a modern system, these task switches can happen hundreds of times per second. Now, to be clear, when we're talking about a system with more than one CPU, say 2, well, each CPU can only be doing one task at a time, but each CPU is running on its own course. So say, while the first CPU is running process A, the other processor might be running, say, process C, or running operating system code or something. And also notice that the intervals at which they alternate their tasks don't necessarily line up. So the mystery here is, how does this scheme work? If a CPU is executing, say, process A, what causes it to stop executing A and switch to doing something else? Well, first off, notice that there's an important pattern here. When we're switching between the tasks, we're never switching directly from one process to another. The operating system always gets at least a little bit of time to run in between processes. This is how things work in what is called preemptive multitasking. Preemptive here means that the running code, namely the running processes, can be interrupted in the middle of what they're doing and be forced to give up the CPU. These interruptions occur, unsurprisingly, when the CPU receives an interrupt signal. And recall, when the CPU receives an interrupt signal, it first saves the state of whatever registers it needs to so that it can come back and resume whatever code it was executing. Then the CPU jumps execution to the handler which corresponds to the interrupt signal it received. And then the way these handlers should work in a modern operating system is, after they've done whatever business is appropriate to handle the interrupt, they then invoke the code in the OS which is called the scheduler. The scheduler is so called because it's the piece of code which decides which process should get to run next. When the scheduler makes its decision, it then sets everything up to prepare to run the process it has selected, and then it simply jumps execution to that process, thus resuming that process. So obviously, for this scheme to work, the operating system has to keep around a lot of data concerning a process, including whatever state information is necessary to resume that process. An interesting question, though, is how the scheduler makes its decision. Well, a reductively simple scheduler would simply go through the list of processes and let them each just take a turn round robin. But that's a naive solution, and it's generally not the best for performance. Ideally, a scheduler somehow tries to prioritize the programs which really need CPU time more than others. Like, for example, if a user is playing a game, but at the same time they're also running another program which is, say, downloading a file in the background. Well, the user's experience is probably best served by giving the game a near monopoly on CPU time. This is because if the game gets starved for CPU time, then the game may start stuttering and become unplayable, whereas if the downloading program gets starved for CPU time, well, that may delay the download a bit, make it take a bit longer than it otherwise would, but typically it wouldn't really matter all that much. A program which is downloading a file is actually going to be spending a lot of its time just waiting for data to come across the network, and so it generally doesn't matter if such a program gets relatively small amount of time on the CPU at irregular intervals. Finally, you may be concerned here about a scenario where the CPU doesn't receive any interrupts for some long interval, and so then you would end up with one process monopolizing the CPU and never giving it up. Well, one reason this wouldn't happen is that typically in a system you do have interrupts firing on a rather constant basis. But just in case, to avoid scenarios where we just happen to have a long dry spell of no interrupts, say on the order of a few seconds or so, systems have an I/O device called a clock, which is basically just a chip that sits on the motherboard and at a very regular interval, say like about 500 times per second or so, sends an interrupt to the CPU. So this clock effectively guarantees that the scheduler is going to be run at least some number of times per second, thereby giving the operating system an opportunity to switch to a different process.